we're talking about lumped element matching networks. And so in lumped element matching networks, it's very important to remember that only lumped elements are used, and that necessarily means we're working at relatively low frequencies. Anything at high enough frequency basically is not a lumped element anymore. So realistically speaking, frequencies that are less than between 6 to 10 gigahertz are okay for lumped elements. And essentially, the higher the frequency, the worse the performance will be, and the harder it is to actually find a component that can actually perform well. Usually, the issue arises from the inductor, since inductors at high frequencies have too many parasitics and severely penalize performance, so you can't really use them very well. So keep in mind that usually below 6, sometimes you can push it above maybe 8 or 9 gigahertz. You can actually rely on having lumped element matching. Now, if I look at this lumped element matching network, the key thing to realize here is to basically ask the question, what is the load that can benefit from having a shunt capacitor? And we already answered this question in my previous discussion. So the load that can actually benefit from having a shunt capacitor will have an admittance that will be of the form 1 minus JB. Because the capacitor can only add a positive admittance, which basically means that if I can arrive right before my capacitor with a negative admittance and a real part of 1, then I can be matched. So again, the key thing to realize is that any load that looks as 1 minus JB in the admittance domain can actually be matched by a shunt capacitor. And so that basically means that my YB on the Y Smith chart must be somewhere here. Right? So on my Y Smith chart, my YB 1 minus JB must be there. Which essentially means that on my, and I think I have actually right here, which basically means that on my Z Smith chart, if I rotate this by 180 degrees, I'm basically going to be on that circle. So essentially, my ZB must be on this locus here if I'm going to be matched. And so my ZB is essentially the impedance right after my series inductor. And my series inductor can only contribute a positive reactance, which basically means that I can only start from a load somewhere here, or somewhere here, or somewhere there, or somewhere there. I can add a positive reactance until I land on this circle. As long as I can land on that circle, any of those loads basically will be matched. But if I'm here, I can never hope to be matched by these inductors because this inductance will only drive me to a higher reactance no matter how small or how large of an inductor I use, which basically means I can never be matched. So the happy region that this network can actually work is the region I saw here with the happy faces. Essentially, it means that any load that has an impedance in this region here, so any load ZL in here can be matched, but any of the other loads here cannot. So in a very similar logic, and I'll let you read this yourself from my notes, in this LC network is exactly the opposite. And essentially, any load that is here can be matched, and the other region cannot.